Hi guys, welcome to the 10th video in the Math 9 ASI series. Today we're going to review inverse functions, take a look at how we can differentiate them, and then move on to L'Hopital's rule, which I think is actually really fun. I enjoy that topic. Okay, so let's just go ahead and get started. Starting off, we're just going to review inverse functions. So we have if a function f of x is 1 to 1, then there exists a function f inverse of x such that if f of x equals y, then f inverse of y is equal to x and vice versa. So if f of y equals x, then f inverse of x equals y. And don't worry too much about the definition of 1 to 1 if you don't know it. Just basically understand that every input to our function is sent to a different unique output value. So if you have two input values, x1 and x2, they're like different numbers altogether. We're never going to have the f of x1 is equal to f of x2. They're always going to be different. So this is kind of just saying that our output values are always unique. We're never going to hit the same one on two different x values. And also note that because of this, these two identities hold true. That the f inverse of f of x is equal to x, and the other way around, f of f inverse of x is equal to x. And also note that f inverse of x is always a reflection of f of x across the line y equals x. So here on the left, I have this function y equals x squared. You see that we look kind of like this over above 0. And then we have our line y equals x. And then our inverse of y equals x squared is y equals square root of x, or y equals x to the 1/2 power. And we notice that it's just reflected across this line, right? You can see this is the same, but just reflected. And then they meet at this point here at 1, 1, and they reflect on opposite sides they were prior. Okay. So let's take a look at how to find inverse functions. Recall to find an inverse function, the inverse of a particular f of x or y, we simply need to swap the positions of x and y and then solve for the y to get the inverse. So we're going to take a look at that example right now. So this is our first example. This is just going to be reviewing how to find the inverse of a function. So the first step is, this is our original function. All we need to do to start off is just swap the positions of our x's and y's. So this becomes x equals y plus 2 over 3y minus 4. And from here, if we want to solve for this inverse function, we just need to solve for y, get it isolated by itself. So let's do that. Let's start by moving this 3y minus 4 to the other side by just multiplying it to both sides times x. It's going to cancel out on the right so that we're just left with y plus 2. Let's distribute this x. We have 3xy minus 4x equals y plus 2. And then we want y by itself, so let's move everything with y to one side and everything without it to the other. So we'll have 3xy minus y equals 4x plus 2. And then we can just pull out this y through distribution. This is 3x minus 1 equals 4x plus 2. And then we can just divide that whole part over so we can get y by itself. So it's 4x plus 2 over 3x minus 1. And then we just replace this y with our f to the negative first power of x. 4x plus 2 over 3x minus 1 to denote that this is the inverse of x. And this is our final answer. So now that we looked over a little bit of inverse functions, now we can look at how to derive them. So since we already know how to find inverse functions, all we need to do is find the inverse and derive, right? In a lot of cases, yeah, it is as simple as that. But sometimes we run into cases where either it's too hard to rewrite in terms of just f inverse of x on one side, all the x's on the other. So in that case, we might have to differentiate implicitly. Or if there's a case like sine inverse of x, we might not even know how to take the derivative of that at all, but we do know how to take the derivative of sine of x. So maybe taking the derivative of that and using some identities is more helpful there. In these kinds of situations, we can also use this identity that the derivative of f inverse of x is equal to 1 over the derivative of f inverse of x. So we're taking the derivative of the original function and we're just plugging in the inverse instead of x into that function, okay? So for this example, I'm going to go over how to use both just deriving the inverse function once we find it, and one way of just plugging into that identity we just learned, okay? So now we want to take a look at how we can differentiate the inverses of functions. And I'm going to go over two different ways with this one problem. So this is the same example as we used before. So we already know the inverse here. So I'll skip that step and just write it down. We have that the inverse is equal to 4x plus 2 over 3x minus 1. I think the easiest way is to just, at least in this situation, is to just take the direct derivative right here. So all we need to do is just do the quotient rule. So let's do f to the negative 1 x derivative is equal to. So I'm using the same thing that I talked about when we first learned quotient rule, that little thing to remember. So I do low d high. So we have 3x minus 1 times the derivative of the top, which is just going to end up being 4, minus high d low. So just the top, 4x plus 2, times the derivative of the bottom. So d low is times 3, all over the low squared is 3x minus 1 squared. And you can simplify this if you want, but the problem is just asking us to find the tangent line. So we don't care about making this pretty. We can just plug in x and find what our slope is at the point that we're looking for. And we're given that x is equal to 2. So let's just go ahead and plug that in. We're going to get, plugging in here, we're going to get 3 times 2 is 6 minus 1 times 4 minus, this is 4. 4 times 2 is 8 plus 2 times 3 over 3 times 2 is 6 minus 1 squared. Simplifying this out, this is 6 minus 1 is 5 times 4 is 20 minus 8 plus 2 is 10 times 3 is 30 all over 6 minus 1 is 5 squared, which is 25. We're going to get that this is negative 10 over 25 or negative 2 over 5. So there is our slope. Before we write out the equation of the tangent line, I want to show you real quick how we can do this using the identity, that equation we learned on the previous slide. So now we're going to solve the same problem, or at least find the slope at this point using our identity we learned before. In this instance, I would say it's probably easier to do it the other way, but really you can do it either way. And I want to show you both methods in case you need it, because some problems are going to require you to use one or the other. Okay? So in this case, and rather than taking the derivative of the inverse directly, we're going to take the derivative of the original function, and then we're just going to plug the inverse into it. So here's our original function, and we can just go ahead and do a quotient rule to find that derivative, much like before. But now we have this function. So we have low d high. So this is 3x minus 4 times the derivative of the top, which is just 1, minus high d low, which is x plus 2, times the derivative of the bottom, which is just 3, over the bottom squared. And before we do anything else, I think it's actually going to be pretty handy to simplify here. So we have 3x minus 4 minus, if we distribute everything, then we're going to have minus 3x minus 6, right? And we see that these 3x's are actually going to cancel here. And we're just left with this. No, that's a squared, sorry. Minus 10 is minus 4 minus 6 over 3x minus 4 squared. So continuing on, this is just our derivative f prime of x that we just found. So now we need to do this 1 over f prime, and then we need to plug this inverse function in for our x, okay? So it's a little weird, but you'll see that it's all going to come together and be the same as we had before. So plugging in that, we're going to have 1 over negative 10 over 3 times, okay, so now we have to plug in the whole inverse, which is 4x plus 2 over 3x minus 1. I'm realizing this minus got cut off here. And that's going to be minus 4 squared. Now we can just go ahead and plug in our x. Instead of making this look nicer, we can just plug in our x now. So recall that our x was actually 2. So plugging in for this, we can go ahead and flip things over because we have 1 over a fraction. So let's flip it up. I'm going to write over here for more room. So we have 3 times 4 times 2 plus 2 over 3 times 2 minus 1 minus 4. And this whole thing is squared because now we're over the minus 10. And if we just calculate this, we're going to get that this is equal to 3 times, that's 4 times 2 is 8, plus 2 is 10 on top. 3 times 2 is 6, minus 1 is 5. So this whole thing is 10 over 5 is just 2, right? Minus 4 squared over minus 10. So this is going to be 3 times 2 is 6 minus 4. So that's 2 squared over minus 10. Or 4 over minus 10. Or minus 2 over 5. Right, and that was the same slope value that we got before. So just showing you could do it either way. Wouldn't recommend this way for this problem, but certain problems, this is going to be a lot easier to do. Okay, so now we're on the final part. Here's all the elements we have. We found this derivative of the inverse, and we have our x point. So the last thing to write our tangent line and point slope form is to find our y value, and we can just do that by plugging into the inverse, okay? So plug in for 2, we have 4 times 2 plus 2 over 3 times 2 minus 1. The top is just 4 times 2 is 8, plus 2 is 10, over 3 times 2 minus 1 is 6, minus 1 is 5. That we get the y point is also 2. And now we can just use our point slope form formula. So we have y equals our slope m times x minus x1 plus y1, with x1 and y1 just being our points, right? So we have that y is just equal to negative 2/5 times x minus 2 plus 2. And you can try, I think it's actually really cool to try plugging everything we found into Desmos and seeing the results. If you plug in like our inverse function and we plug in this tangent line, you can see that everything's going to line up properly. Okay. Finishing off, we have L'Hopital's rule. We have one of the following situations where the limit as x approaches c of f of x over g of x equal to 0 over 0, or if we have a limit of that form is equal to plus or minus infinity over plus or minus infinity, then we know automatically that this limit of f of x over g of x is equal to the limit of f prime of x over g prime of x. This is a super handy result, but keep in mind we can only use this in one of these two situations. So there might be some cases where we can't use L'Hopital's at all, or sometimes we can manipulate the equation to get it in the form that we want it to be in. We're going to look at 2 more examples, and then we'll be done for today. So here's our first example of L'Hopital's rule. So the first thing we want to do to make sure we can even apply L'Hopital's rule is to plug in our limit and make sure that we either have 0 over 0 or infinity over infinity. So let's go ahead and try plugging in 1. If we plug in 1, then everything's going to just end up being, so 5 times 1 to the 4th is just 5, minus, it's just going to be 4, minus 1, over, this is going to be minus 9, minus 1 plus 10. So 5 minus 4 is 1, minus 1 is 0. And then we're going to get minus 9 minus 1 is negative 10, plus 10 is 0. Okay, so we have 0 over 0, so we know we can apply L'Hopital's. So let's go ahead and do that here. I'm just going to write LH. And so we know that this is going to be equivalent to just taking the derivative of the top and bottom. So let's do that real quick. We're going to have 20x cubed minus 8x, and the minus 1 is just going to go away. And then we're going to be left with minus 9 times 3, which is minus 27, x squared minus 1. So now let's try plugging in 1 here and seeing if we get a different result. So plug in 1, we're going to have 20 minus 8 over minus 27 minus 1, which gives us 12 over minus 28. Simplifying that a bit, that's going to end up being, I believe, 6 over 14 divided by 4. This is 3 over 7. Okay. That's the final answer. And finally, here's our last example. So we have the limit as x approaches infinity of x to the negative second power times natural log of 3x. So looking at this immediately, if we plug in infinity, we're going to get x to the negative 2 is 0 as x approaches infinity, times natural log of 3 times infinity is just going to go to infinity. So we can't really do anything with it like that now. But what we can do is just rewrite this. And this is a not too bad version of this kind of problem. So if we rewrite this, we're just going to have natural log of 3x over x squared, right? Since if it's a negative power, we can just move it to the bottom and take away the negative. So we're left with that. And now if we plug in infinity here, we know this is infinity on top, and then infinity squared is infinity on the bottom. So now we have it in the right form, and now we can apply L'Hopital's rule. So let's go ahead and do that. Just going to write LH to denote that again. So we have that this is equal to x approaches infinity. So the derivative of the top is going to be just 1 over 3x times the derivative of the inside. So this is chain rule, right? So we're multiplying by derivative of 3x, which is just 3. You get that these 3's cancel. And then the derivative of the bottom, x squared, we know is just 2x. So we have 1 over x over 2x. This is the same thing as the limit as x approaches infinity of 1 over 2x squared. And now if we plug in the bottom, we're going to get just infinity on the bottom, 1 on the top. And we know that that's going to go to 1 over infinity is just going to go to 0, right? Because the bottom is increasing with no limit, and the top is just remaining constant. So it's going to approach 0. Okay? Please let me know if you have any questions. This isn't all easy stuff, especially this inverse differentiation. So if you need any help at all, I'm always happy to help out in any way. Thank you for watching. Please sign in too if you can. Yeah, have a good weekend, and I'll see you guys next week then. Bye.